Dear ladies and gentlemen, welcome to today's webinar. My name is Michael Wenzel and I would like to talk about materialographic sectioning, the basic concepts and consumables in the following 40 to 45 minutes. We will talk about this agenda here. At first, I would like to review the materialographic sectioning process. I will list some analytical goals for which this process is used. Then I will give an overview about differing sectioning techniques and then focus on wet abrasive cutting, the process itself, and defining parameters. We will then continue to the variety of cutting machines and the usable consumables. I will elaborate differing cutting modes as well as give a short overview over the anti-corrosion coolants used as well as the cut-off wheels in application. Then the main focus of the webinar is reached. We will talk about application examples as well as common mistakes and tips on how to prevent these mistakes from occurring in industrial application. We also will highlight some advanced clamping solutions for specific part geometries. So let's finish everything with a summary so that you also have something to take home with you. Let's begin with the analytical goals. Here we see some section samples, and of course we usually generate cross or longitudinal sections of either complex assemblies or parts of simple geometries such as round steels, for example. We also may work with processed or coated parts as well as natural products like minerals or other even organic samples like woods or polymers, as well as composites. Commonly, we remove a critical or small part for a variety of reasons, one being the materialographic sample preparation or the failure analysis of a part. Also, for some chemical analytics like optical emission spectroscopy, the sampling of smaller parts may be necessary to generate a sample that can be handled in the lab. Also, samples for mechanic testing methods such as dynamic mechanic analysis or tensile testing are cut from larger materials, for example, from metal sheets. In general, we can say that the main analytical goal of the wet abrasive sectioning process is the sampling of a solid with a reproducible dimension and acceptable time frame. So which sectioning techniques are present on the industrial and scientific market for the laboratory? At first, we have the mechanic sectioning processes, which are the most important ones. And wet abrasive sectioning is the most common of these techniques. It's suitable for the thin sectioning of hard materials and applicable to almost all solids. Some exceptions may be very soft polymers or rubber materials, but even there are applications possible. In general, we observe a very small plastic deformation zone, which is commonly below a depth of 200 microns from the cut surface. And this is quite nice because we then can shorten the grinding and polishing steps drastically because we have to remove less material to reach the true microstructure. However, we cannot carry out any curved cuts or fancy sample geometries. If you need this, you will need to employ a saw, mainly a wire or band saw. These machines are of course not suited for thin sectioning because the plastic deformation zone is much thicker in comparison to wet abrasive sectioning. Here we are talking about deformation zones of 0.5 millimeters. Also, the applicability on very soft and ductile materials as well as very hard and brittle materials such as fired ceramics are limited or at least quite difficult to realize. Finally, we have the microtomy. Here I would only like to talk about the blade-based setup because other microtomic techniques are quite similar to wet abrasive sectioning. This technique is the standard in polymer science and biology, and of course only with a limited applicability on hard and brittle materials since we cut with a defined blade. And therefore it's also only suitable for the generation of thin sections. the most sample thicknesses are below 60 micron. On the other hand, there are also thermal sectioning processes used in material sciences. However, in our context, the context of materialography, these are either not suited for the materialographic application, since the true structure is altered, or they have a too low throughput for the application in an industrial laboratory. To name a few techniques, we observe the use of focused ion beams, of laser cutting, as well as cutting wires in certain niche applications. But how does wet abrasive cutting work? It's quite simple. At first, you clamp the part which may have been previously sectioned to fit in the clamping device and the cutoff machine. Then you choose fitting consumables, set correct parameters, and position the cutoff wheel, and finally start the automated or manual sectioning process. And after you have sectioned the sample, you take the sample out, clean it, and do whatever you want with it. But even though on the first glance this cutting process seems quite simple, it isn't. Here I have gathered a small overview about the most important parameters during this cutting process. And the area of interest is here, the area of contact in which the mechanics of wet abrasive cutting come into play. Also quite important is the content of the cutoff wheel. Here I talk about a binder face and the used abrasive, while the abrasive itself is interesting in regards to grain size, hardness, and chemical composition. The binder also has quite important properties such as toughness, its adhesion to the abrasive, and of course porosity and media resistance. So as already mentioned and most likely known to you, the cutoff wheel is rotating with a certain velocity and generates some abrasive residue, which is constructed out of chippings, which are generated by fixed irregular edges or the abrasive particles still sitting in the binder matrix. On the other hand, we also have the influence of the loose abrasive, which leads to a scratching on the cut area and also influences the cutting process. We always have a multitude of cutting points active across this cutting arc here. Ideally, we work in the so-called free cutting state, which in principle only means that you can enhance the feed velocity without consuming more energy. Modern cutoff machines, you can see this in the menu by constant staying energy consumption of the main motor. And why can this be the case? The widely known G ratio, which is a parameter for the longevity of the cutoff wheel, which in principle just is the volume of the removed material divided by the volume of the removed abrasive per cut, does not vary much in the free cutting state, but it does vary, and therefore we should see a decrease or increase in energy. To understand this, we have to have a look at the so-called specific cutting energy, which is not the total energy measured during the cutting, but an energy that only can be applied to a stationary state where the contact area does not grow too much. This energy is influenced heavily by Ft, which is the tangential force that is needed to push the rotating cutoff wheel through the sample, and of course by the rotation velocity the cutoff wheel has at this certain moment, as well as the length of the contact area or the cutting arc, and of course the thickness of the cutoff wheel, as well as the feed speed. And you see that these two parameters counteract each other, because otherwise ES would never stay constant during the free cutting state. This can be explained by the tangential force being a wheel-specific parameter, depending on the rotational speed of the cutoff wheel, which influences the viscoelastic properties of the binder material, and the feed speed on one hand, as well as the constant specific cutting energy and C, which is a quite important parameter because C equals the amount of active cutting points at a certain moment in time, which increases when we increase the feed rate, which then, of course, leads to a smaller G ratio. But enough about pointless theory. Let's have a look at the parameters you can adjust during the cutting process. Of course, a modern cutoff machine offers the possibility to save methods, and you can switch between manual control and different automatic cutting modes we will discuss later on because they are quite application relevant. You also have to adjust the cutting distance in regard to your part dimensions, can activate a pulsation of the cut, as well as the coolant flow. You also can set some serial cuts where more than one sample is cut from the working piece. Here we adjust the feed rate. We can also set a threshold value for the cutting power, and also can adjust the rotational velocity. Of course, a modern cutoff machine also offers some features that should make cleaning of the machine as well as sample positioning easier. In general, cutoff machines can be divided in three main classes. The first one being the so-called precision cutoff machines, which are well suited for small parts, thin sectioning, and targeted sectioning. QATM offers the QCut 150A or M, as well as the Brilliant 220 in this segment. And these are often found in university laboratories, for example. However, the cutoff machines most of you will work with are so-called tabletop cutoff machines, which are a nice compromise between the precision of a precision cutoff machine and the performance of a larger shop floor machine. And machines like the QCut 250A or M are the most common in the materialographic laboratory. Of course, if you have very large sample throughput or use wet abrasive cutting for non-materialographic use, you may also use a larger dimensioned shop floor cutoff machine like the QCut 600 and 800A, which is has the possibility to cut quite large parts. Since we are talking about wet abrasive cutting, we of course need some sort of medium circulation, and there are different approaches. Especially precision cutoff machines sometimes sport a swamp cooling, which is quite interesting for thin sectioning processes. And here we see an image of the QCut 150A. However, more common is the use of so-called recirculatory cooling units, which are in principle a basin with a pump and a filter insert. Their volumes can range between 15 and 125 liters. And of course, they should be chosen depending on the size of the cutoff machine. Here we are talking about a precision cutoff machine, and with this we are most likely talking about a large tabletop cutoff machine or even a shop floor machine. If you have really high throughput applications with large machines and large cutoff wheels, you also can use a belt filter system, which is more effective than recirculatory cooling units. However, you may have already forgotten the different cutting modes that a modern cutoff machine can use. And many beginners are a bit baffled by their large number. So let's start with the most common cut, the transverse cut, which is well suited for long and flat cross sections, as well as the precise sectioning of very small parts. And this is the case because for this part geometries, the contact area is as small as possible, which is the goal for a sectioning process. You don't want a large contact area between cutoff wheel and sample if possible at all. Therefore, the chop cut always is used on compact samples where the epsilon axis is larger than the x-axis. And if you have very large parts, you combine these two methods in the so-called step cut, which is available with two dominant axes. And of course, you use this for large samples for very hard materials because you not only have a small contact area, but you also have in general a better coolant flow through the cut part. Of course, the axis is always chosen perpendicular to the maximum dimension of the cut part. The diagonal cut is very special. It's only applied if we have to cut through an inclined plane. In this case, we cut perpendicular to this inclined plane. The zigzag cut is an automated cutting mode for heat-sensitive materials, which also tries to minimize the contact area while enabling a quite nice coolant flow. The care cut is the semi-manual alternative to the zigzag cut. It is used if we need really high precision, for example, while cutting very complex assemblies or heat-sensitive materials, as well as compound with strongly varying mechanical properties across the cross-section. This is often the case for laminated material assemblies. Finally, we have the so-called rotation cut, which is always used if we have a rotational symmetry in our parts and have, for example, a porous coating that has to be protected during the cutting process. Now, after we have formed quite the understanding of the process of wet abrasive cutting, I would like to switch to the consumables and talk about the anti-corrosion coolants. Here we see a set for quality control because that's also quite important. The anti-corrosion coolants has the following functions. First, of course, it has to protect the machine and the sample from corrosion. Also, we needed to enhance the abrasive removal and guarantee a certain amount of lubrication during the cutting process. Further additives, often today integrated in the basic anti-corrosion coolant, lead to the precipitation of certain dangerous cations like cobalt or copper, which are environmentally hazardous. Also, the antimicrobial properties of the medium are enhanced, leading to a longer lifetime of the cooling medium. Commonly, the pH value is set between 9 and 10. We also observe an increased boiling point for a better cooling performance in comparison to mere water. The market generally offers aqueous corrosion coolants that form aqueous solutions, which are the most common class of anti-corrosion coolants on the market. And these are also the anti-corrosion coolants QATM distributes. Modern products do not contain any CMR or SVHC compounds like boric acid anymore and are quite safe to use. However, there are also anti-corrosion coolants present that form aqueous solution, especially if you use large shop floor machines with a large sample throughput and very big parts. They have the advantage to carry more abrasive residue in comparison to the aqueous solution, which is the main point for the application because they only have a medium cooling performance and a higher lubricating performance that is bad for the chipping behavior of the wet abrasive cutting process. In some application, we also may have water-free anti-corrosion coolants on a cutoff machine. This is only the case if the cut material is so corrosion sensitive that the cutting in an aqueous medium is not possible. We, of course, have very low cooling performance and a high lubricating performance since we're talking about cutting oils in this case. More important than the choice of the anti-corrosion coolant is the choice of the cutoff wheel. Here we see a selection of fully resin bonded cutoff wheels and steel substrates which have been coated with an abrasive layer. In general, we classify the cutoff wheels according to the abrasive they apply or to the binder system that is used. And the most common segment is the resin bonded cutoff wheel. In this case, mainly phenolic resins and rubbers are used as binder phases, and we encounter 4 different abrasives on the commercial market, which is corundum, silicon carbide, diamond, and cubic boron nitride. Especially if you want to cut very hard materials or in some cases also very soft materials, you use a metal bonded cutoff wheel with differing porosity and grain size distribution. And due to the high cost, we only find the metal binding in diamond cutoff wheels and cubic boron nitride cutoff wheels. The same also goes for sintered or electroplated cutoff wheels. Sadly, I cannot go into more detail about the properties and application ranges of all the different cutoff wheels because that would make this webinar quite long. However, I will give the example of the corundum-based cutoff wheel because that might be the most relevant type of cutoff wheel for you. As you see here, corundum-bounded cutoff wheels can be applied on very different materials with hardnesses ranging from 30 to more than 650 HV or up to 900 in many cases. Usually, corundum-based cutoff wheels are used to cut metals, often steels, cast irons, titanium alloys, copper, and so on. The solution in general is quite cost effective because we don't need a steel substrate, we don't have a very expensive abrasive. Also, we observe a polishing effect, especially with rubber-bounded corundum cutoff wheels because they have smaller abrasives present in them. And depending on the type of binder, we have very different application ranges because the abrasive, of course, is the same, and the abrasive hardness of 2000 HV, of course, restricts the application range of corundum, which explains why we use cubic boron nitride and diamond as abrasives. Another advantage of the corundum-based cutoff wheel is that you can make them very big very easily, and therefore large specimens are also often sectioned while using corundum as an abrasive. As a general rule of thumb for selecting your cutoff wheel for a certain material, you can say a hard material is sectioned with a cutoff wheel that has a soft binder face and hence quite high wear, while a soft material is sectioned with a harder cutoff wheel which has a hard binder face where the breakout of the abrasive takes place slower. And with this, we have already reached the main focal point of this presentation. I would like to talk about applications. And here we see the example of a steel part of medium hardness. We have a quite complex shaft that is longitudinal sectioned using a corundum cutoff wheel for steels of medium hardness. Our circumferential speed ranges commonly between 30 and 60 meters per second. Here we are in the middle with an approximated circumferential speed of 47 meters per second, which of course changes depending on the diameter of the cutoff wheel. Due to the large dimension of the contact area, we use the pulsation feature, which leads to a better cooling performance during the cut and also enables the use of a higher feed speed because in this case the clogging and glazing of the wheel is prevented. The clamping solution is a so-called cross vise, which is a quite cost-efficient solution for this part, which could only be clamped properly using universal vices and a specific plate setup customized for this shaft otherwise. As already mentioned, the traverse cut optimizes the coolant flow into the sectioned parts and protects the case-hardened shell. Also, of course, we can very precisely adjust the coolant supply with these coolant hoses present here. Finally, the clamping device prevents the jamming of the cutoff wheel because even if the part is not properly sectioned, these clamping vices prevent the pressure of the sample on the cutoff wheel during the cutting process and hence the breakout of the marginalized layer. Also, the shaft, of course, can be sectioned in perfect symmetry, which is an advantage of this clamping solution. More common are so-called fast clamping vices you see in this picture. Here we are cutting a heat-treated steel part with a hardness of roughly 60 HRC. We use a quite soft corundum-based cutoff wheel, the FSE cutoff wheel, and also have a slightly lower circumferential speed, which enhances the wear of the cutoff wheel, which can be good for sectioning a hard material since we have more of a polishing approach on the cut surfaces. We also apply pulsation to guarantee a good cooling and have a feed speed of 1 millimeter per second. This clamping solution is quite versatile and cost efficient, especially in case of the clamping vise 80, which allows the adjustment of these clamping inserts in this and this direction, as well as the exchange of differing clamping inserts for the fast clamping vise. If we want to ignore this pulsation because we want to have a higher sample throughput, we have to slightly lower the feed speed to maintain a good cut quality. Now I would like to switch to a very different material, to a copper alloy, which you see here as a profile, which is clamped in between two clamping vices that have been aligned. In this case, we use a silicon carbide cutoff wheel with a lower feed speed. In this case, we focus on a high quality cut. If you only want a fast cut where burr formation is tolerated, you can go to higher feed speeds of up to 2 millimeters per second. The clamping solution is quite fast and reliable, and in general, high feed speeds and low circumferential speeds prevent the clogging of the cutoff wheel while cutting very ductile materials, especially if the porosity of the cutoff wheel is not that large. These are quite common parameters for soft and ductile materials, which most likely could also be applied to aluminum alloys. And with this, we already have reached the last application example, which would be the cutting of a ceramic. And since this oxidic ceramic, it's an aluminum oxide, is way too hard to be cut by the corundum, we have to use a diamond-based cutoff wheel. In this case, it should be a resin-bonded wheel. We have a quite low circumferential speed of approximately 20 meters per second, as well as a lack of pulsation. This is done to prevent the breakout of ceramic parts, which is a real big problem in the case of sectioning brittle materials. Therefore, we also have applied the trick of using a sacrificial plate and this special clamping setup that allows the rotation of the sample and hence a very precise arrangement of the clamped sample, which is only this part. Also, we use a chop cut to minimize an acentric load on the cutoff wheel, which may lead to a run out, which is quite detrimental while cutting such a brittle and material with high internal stresses, which is the case for almost all ceramics you encounter on the market. The clamping solution, of course, is quite easy to handle, and it's a fast and reliable solution. And with this, we already have arrived at the collection of application errors. Here you see an oxidized cut steel. And of course, this oxide layer formation is most likely related to an insufficient cooling performance during the cutting process. You also observe a plastic deformation. And we see that we have to adjust the coolant flow, or we have to check if the coolant flow is present. Otherwise, we have to drastically reduce the feed rate during the cutting process, because then this part was cut way too fast. We also have to adjust the cutting distance, because otherwise we will still see either such plastic deformations or a not totally cut cross-section of the sample. Many of you may also have encountered the run out of the cutoff wheel. Here we see that the cut has lost its plane parallelism, and also the wheel has jammed and is in danger of breaking. Common countermeasures are, of course, a realigning of the clamped sample, maybe the change of a cutoff wheel if it has already been damaged. Also, you, of course, have to repeat the sectioning process. And if you look at a damaged cutoff wheel by run out, you will see that only on one side you can see these smear marks, while the other side of the cutoff wheel still looks pristine. The more extreme variant is depicted here. We have the fracture of the cutoff wheel, as well as an unfinished sectioning process and the dislocation of the damaged part geometry. In this case, you most likely would have choose a stronger clamping device or adjust the cutting parameters so that less pressure is generated on the cut cross section. Also, of course, sample and reel have to be properly aligned before the cut is started. Glazing of the cutoff wheel is a quite common issue, especially which is caused by an excessive heating of the sample, or more precise, the area between sample and cutting wheel, we see this sparkling finish, which is due to a partial melting of the abrasive grains. To prevent this from happening, you should choose a softer cutoff wheel. You also could reduce the rotational velocity or dress this damaged cutoff wheel with a hard sample, most likely a ceramic. You also have to check if the coolant flow was properly adjusted during the cutting process. There are, however, some errors restricted to targeted preparations or to precision cutoff machine. If we want to make metallographic cross-section of this capacitor here, we cannot use a thick cutoff wheel like depicted in this picture, because the electronic assembly here will be destroyed during the cutting process, and of course our target preparation is impossible. To prevent this from happening, we could have mounted the sample in epoxy resin previous to sectioning, or we could use a thinner cutoff wheel with a protective flange that stabilizes it against runouts, to which such very thin diamond cutoff wheels with diameters of maybe 0.3 millimeters, thicknesses of 0.3 millimeters, excuse me, are quite prone. So which type of errors can be generated by the wrong setting of a certain parameter? Let's sum up. Too high rotational speeds can lead to glazing and clogging of a cutoff wheel. It may also lead to excessive wear and the embedding of abrasive grains in the material. Also, you may observe a friction-induced heating of the sample and hence microstructural changes. The same goes for too high feed rates, where we also additionally see the deformation or fracture of the cutoff wheel and of course the runout that may occur, as well as the friction-induced jamming of the cutoff wheel in the sampled cross-section. The wrong coolant composition or wrong coolant flow rate may lead to the formation of oxidic layers on the part surface. It may also enhance the plastic deformation during the cutting process and lead to microstructural changes. Corrosion and dissolution also may occur, and the dissolution is especially a problem if you are sampling polymeric materials. If you use the wrong clamping solution for a certain sample, you can observe the jamming of the cutoff wheel, deformation or stress-induced cracking of the sample, as well as a loss of plane parallelism. And in some extreme cases, the sample is even removed from the clamping device. So advanced clamping solutions are quite important. And I would like to show you some quite simple tricks, like the use of two aligned fast lock vices mentioned previously. These minimize the risk for a runout and also prevent the jamming, especially if you have a part that has internal stresses due to a shaping process like forging or die casting. Also, the burr formation is strongly reduced, and we may reduce the risk for spontaneous fracture if we have a brittle material. Brittle materials also should be mounted on sacrificial plates if possible at all. And the reason for this mainly is that the pressureless clamping of a brittle material is the only way to ensure that no breakouts occur, which is not guaranteed, by the way. Also, the plane parallelism is quite strongly enhanced compared to a sacrificial plateless cutting of the same material as you see here. The a clamping solution based on a chain adjuster is also quite interesting for the clamping of large parts with non-geometric profiles like this brick. It's a cheap alternative to a matrix clamping device like the X-Clamp 3858, even though it's less versatile. Matrix clamping systems offer this solution based on spring-loaded pins, which enables the clamping of very complex geometries. Here we see the assembly centered around a universal clamping vise that has been fastened on QATM's easy clamping system L with a setup of swivel units that allow the rotation in two spatial directions and hence a quite free and reproducible spatial arrangement of the quite complex sample. This is a quite cost-effective alternative to robotic clamping systems that are also in application in the industry. Here we see the example of the QATM Brilliant 3D setup. Also, automated rotatory clamping devices are used if we want to section spheres or coated parts. With this, we can carry out automated rotatory cuts, and this is of course ideal for the protection of coated parts, as well as for rotation symmetric parts that are quite sensitive to heat influence. If you have to sample a lot of plate material, for example, you want to cut prepregs plates into tensile testing bars, you can use such a pulsed clamping system, which has been optimized for the automated sectioning of plates. It's very fast and reliable, and shows a pneumatic feeding mechanism that enables the movement of the material in this direction, because this array is pushed forward, grabs the material again, and drags it back. With this, we have already reached the end of my presentation, and I would like to summarize what you should take home with you. Let's talk about general rules of materialographic sectioning. Usually, materialographic sectioning for laboratory applications is used by applying wet abrasive cutting. Also, artifacts generated during this step in the materialographic workflow are quite difficult to notice during the later preparation steps. Therefore, you have to take care that you apply the right consumables and parameters, because otherwise you may introduce a systematic error in your system and you will, of course, never notice it. The most important parameters for wet abrasive cutting are the feed rate, the circumferential velocity of the cutoff wheel, as well as the cutting mode. And of course, the choice of cutoff wheel and cooling medium, as well as the use of the proper clamping device. Clamping devices come in various sizes and shapes. Fast clamping devices and universal clamping devices are really versatile tools. No laboratory should miss. However, there are applications that require very specific and customer-oriented clamping solutions, and I hope that I have given you a short insight in that matter. There are also mostly manual and automated clamping variants available on the market. And with this, I would like to thank you for your attention. Before you leave, I would like to add that you can send questions to Michael Wenzel at QATM.com. Please add the subject webinar materialographic sectioning. You also may directly contact your area sales manager or your local distributor. Our next webinar, also mainly addressed to beginners in the materialographic field, will be dealing with materialographic mounting, its basics and applications. It will be held on Wednesday, the 26th of May from 9 to 9:45 a.m., as well as from 4 to 4:45 p.m. European Standard Time. Thank you very much for your attention, and I hope to see you again next time.